you know, like I think it was like number of doctors' visits regressed on things like, you know, health status or something like that. So we talk about continuous versus continuous. Well, we can also do regression with dummy variables, binary variables, right? So we're going to use the same data set that we did before where we looked at the rats and the amount of food that they ate. But this time what we're going to do is we're going to ask very specific questions of the data. When we did the ANOVA before, we didn't have any, you know, we pretended that we didn't know anything about the data, so we were going to do all post hoc tests. We were going to ask the question, I don't know what's going to be different from what, so I'm going to look at all possible pairwise comparisons. And the one thing that we learned was that when you look at all possible pairwise comparisons, there's going to be a big penalty to pay, a big statistical penalty by making it harder to reject any pairwise difference. So what I want to talk about now is how to do the ANOVA in a regression framework. And in doing so, we can ask very specific questions of the data. Okay, very specific questions of the data. So I'm not going to take the time to review the the univariate statistic, the descriptive statistics for the data set, because we're going to deal with the same data set as we've done before. But the one thing I am interested in looking at here is that too small for you guys? Yeah, that's too small for me. I'm looking right at it. What I'm going to do now is I'm going to write down the means for these groups, because what I want to show you is that with regression, regardless of how we parameterize the regression, we're all going to get back to the same means. Okay? So the other thing I asked you guys to think about the other time was when we first did the ANOVA, we treated the dependent variable, the factor, as purely nominal, right? So nominal data are simply different in kind. So we're saying that daily is simply different from weekly, and weekly is different from biweekly, and so on and so forth. But we've ignored the ordinal nature of the data. Make sense? So if we thought about the data a little bit more, we might say, well, here is none, some, more, most, right, in a very broad, coarse sense. So if we think about it, none, some, more, most, then we have this concept of order in the data, or greater intensity of the intervention. So if we begin to think about the property of our data, we might be able to ask more specific questions of the data. So now that we've written this down, let's get into the regression model a little bit. The first model that I want to look at is something called a cell means model. A cell means model, right? So let me show you how to do that, and then we'll talk about what it is. So here we have a cell means, what we refer to as a cell means model. And let's look at, let's take a look at the output here. You can all see this okay? It's a whole lot better than what we had before? Okay. First of all, let's ignore all of this up here. Let's pretend this doesn't exist. Does anybody see something missing from the regression table? Right, the intercept's missing, right? Does anybody see anything interesting about these coefficients? Those are the means, the group means, right? Those are the group means. Now, why am I talking about this cell means model, right? I'm talking about this cell means model because I can use regression to get the confidence intervals for each of these means directly. Right? Because I have a coefficient here, and we looked at these coefficients are the same as the means, right? And then I get a confidence interval for each of those coefficients. Right? Now, why am I showing you this? Well, the reason I'm showing you this is because if I were to compute a confidence interval based on the original data, 4 observations would have gone into this 3, 4 observations would have gone into this 4, and 6 and 9 respectively, right? So if I were to compute a standard error and then a confidence interval around that mean of 3, right, it would be the standard deviation divided by the square root of n, right, times some t critical value based on 3 degrees of freedom. Right? Because I had 4 observations. What's happening here, what's going to happen here with this data set is that all 16 observations are going to go into predicting this 3. All 16 observations are going to go into predicting this 9. And how many degrees of freedom have I used? I've used 4, which leaves 12 degrees of freedom left over. This becomes the denominator of my standard error. So if I divide which confidence interval do you think is going to be tighter, the univariate or the confidence interval coming from the regression? It's going to be tighter coming from the regression because I have more observations going into the prediction. Right? And when we do a univariate, even when we do a mean, it's still in some sense a prediction, right? When we wrote down that model, we wrote it down this way. It's a prediction, right? So this is really just a prediction without any predictors. Right, in the univariate sense. Now we have some predictors here, and what have we learned when we want to predict something and we have something to predict it with? We learn that our precision of those predictions get better. They get better. Okay? So this is the code that I would use to create this cell means model here. So this is sort of our first foray into this idea of the real power of regression. Okay? The real power of regression. Oh, and that's scratching back. Now, most people, when they do regression, or they do an ANOVA using regression, they're going to use the default values of the software. And the default values of most software is to do what we refer to as dummy coding. Dummy coding. So what's going to happen is, let's talk about it this way. So in this data set, we have people who are taking the drug daily, weekly, bi-weekly, and then they're taking a placebo. Okay? So in general, if I have k levels of a group, in this case k equals 4, right? I'm going to need k minus 1 indicators in my regression model to determine what group a particular observation belongs to. Okay, so what's going to happen here is I'm going to have an x1 variable, an x2 variable, and an x3 variable. Okay? So what we can do is when we use dummy coding, our hypothesis becomes a little bit different. When we did the ANOVA before, we wrote down the null hypothesis as being mu I equals mu j for all I less than j. Right? We wrote it down that way. Now let's pretend that we know something a little bit about the data. And I don't want to do all possible pairwise comparisons because I know there's a heavy penalty to pay for not being specific with respect to my hypothesis. So what we want to do now is I want to introduce you to this concept of a priori hypotheses. So what does a priori mean? It means before the fact. That's what it means. So what we're going to do now is, instead of doing all possible pairwise comparisons, let's take a look at our data. All right? So we have daily, weekly, bi-weekly, and placebo. If you were to guess, or if you were interested in determining whether or not your medication was effective at decreasing food consumption, is there one of those groups you might want to compare your active substance against? Placebo, right? So in that case, instead of doing 4 times 3 divided by 2, 6 pairwise comparisons, might you want to be a little bit more frugal and compare daily versus placebo, weekly versus placebo, bi-weekly versus placebo, and that's it? You might be able to do that. So in that case, what we're doing is that we are now treating placebo in a very special way. We're going to treat it as a referent group, right? So with our hypotheses, and our hypotheses using dummy coding, we're going to ask the question, that very specific question, is daily different than placebo? Is weekly different from placebo? Is bi-weekly different from placebo? And we don't even care about these pairwise differences. We're not interested in that. So in that case, we're only testing three hypotheses. Okay? So let's see what the default behavior is in Stata. So to do this dummy coding in Stata, the codes that we're going to use is the following. So I'm going to use a prefix command called xi. Xi sort of tells Stata that you're going to create dummy variables. Right? So, okay, Stata, wake up, get prepared to create a dummy variable. And then we have regress, as you've used before, and we have our dependent variable food. And then here you see I.drug. The I dot tells Stata that this is a factor. It's a factor and it's not a continuous variable. So what it's going to do is it's going to expand drug into k minus 1 levels. Right? And we'll see what happens. Okay. So let's take a look at our regression here. Oh, by the way, all of these p-values will be exactly the same. All this stuff at the top will be exactly the same as we did when we did the ANOVA. But because we're interested in asking a very specific question, we can essentially ignore this. Because this is what we're going to be interested in when we're looking at all pairwise comparisons. Okay? Okay, so what happens here is now I have an intercept that's 3. How would I interpret that intercept of 3? Well, it's when all values of x are 0, that's the expected value of y. So Stata doesn't tell you what's 0, what's 1, any of that, right? It doesn't tell you. So what I'm going to do here is I'm going to scroll down. And what it did for us, what Stata did for us, was it created 3 extra variables for us. It created 3 extra variables for us, right? So it created anybody who was, well, this is what it did. Let me explain what it's doing here, okay? So what it did for us is that it chose our referent group for us. Right? It chose our referent group for us. So let me label this here. Right? So you see this is full of zeros and ones here. Right? 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1. Right? Got that? What it's done is this has created what's called a contrast matrix. What does it mean to contrast something? Differentiate, compare against, something like that. I like that. Differentiate is actually really good mathematically. I like that. A+, star, gold star. Okay. So what we're going to do here is we're going to create a matrix of zeros and ones to help us contrast one level of the factor against all other levels. Right? So what we're going to do here is we get to choose what we want to have to be our referent group. And we said that we were going to choose placebo to be our referent group. Okay, so let me show you how this works. All right, so this is going to be simple algebra. So what we're going to do is we're going to write down our model. Oh, there we go again with our crazy models. And by the way, this is going to be the same model we use, regardless of how we parameterize the model, right? So here we have beta 0, which is going to be our intercept, and then we have x1, 2, and 3. We're going to need an x for k minus 1 for each of the k minus 1 levels of our factor. Okay? So the first thing we need to do is we need to choose what level of our factor do we want to contrast the other levels with. So we decided that we're going to compare all of the other levels against placebo. Okay? So the first thing we're going to do is for the placebo line in our contrast matrix, we're going to write down zeros for all of the columns in our placebo row. Okay? And then what we're going to do is we're going to say, okay, we're going to decide what our x1 variable is going to represent. Right? And I'm going to arbitrarily say that x1 is going to represent the rats who receive the drug daily. Right? So is did the rats who took the drug weekly, did they take it daily? No. So I'm going to give those guys a 0. Right? And we know that placebo isn't daily, so that's going to get a 0. All right? And what do we want x2 to represent? We can let it represent either weekly or biweekly. We want it to represent weekly. Okay. So I'm going to give that a 1 in the x2 column. Okay? So is daily equal weekly? No. Is biweekly equal weekly? No. Okay? And then finally, we're going to end with this. Okay? So let's go through this row by row. Okay? So if we're going to say x1 is going to represent whether or not you've received the drug in the daily group, right? So if I multiply x1 times 1, that means that you're in the daily group. If 0 times x1 means that you're not in the daily group, right? Okay. x2 times 0 means what? Not in the weekly group, right? x1 times 1, or x2 times 1 means that you're in the weekly group, and so on and so forth. Got that? Now, why do I need k minus 1 indicators to fully represent k levels? All right, so let's look at this here. So if my x1 is 1, that means I'm in the, and not in the other groups. If x2 is 1, that means I'm in the, and not in the other groups. And x3 equals 1, that means I'm in the, and not in the other groups. So if for placebo, if you're in the placebo group, and your x1 is 0, what does that mean? Not daily. Your x2 is 0, that means not weekly. x3 is 0, that means you're not biweekly. So if you're not daily, not weekly, not biweekly, then you must be in the placebo group. That's why you need k minus 1 levels. Okay? So by manipulating this contrast matrix and actually understanding how this works, you don't have to accept the default values or default behavior of your software. Because different pieces of software will give different levels of your factor the status of that referent group. Okay? And that's really important. Because in the end, when it kicks out the data, when it kicks out your information, we can now fully, these slopes now become very easy and interesting to interpret. So the what Stata does by default is that it's going to set the lowest level as the referent group. So here, if all of these things are x, then 3's got to be the expected value for the referent group. So what is 3? 3 happens to be the mean for the daily group, right? So let's look at these things in turn. 3 plus 1 equals, which happens to be the mean for the weekly group. 3 plus 3 equals, which happens to be the mean for the biweekly group. So when you do this regression using dummy variables, these coefficients, the regression coefficients, these slopes, they become the difference between the group means. Does that make sense to you? All right, let's write it out, okay? Let's pick a group. Let's pick groups. It doesn't matter which group we pick. Let's pick a group and we'll plug them into these values here. You'll see how this works. Pick a group.
Group 2.
You want to group 2, that's the weekly group, right? Okay, so if I write down my model, so beta 0 is what? That's our intercept, right? Our constant. That's going to be 3 plus beta 1, which is 1 plus 1 times x1, plus beta 2 is 3 times x2 plus 6 times x3, okay? x1, right? So we wanted to do the second group, drug 2, right? So that's going to be the daily group. So the daily group is going to be yi equals 3, because that's our constant. What do I have to add to 3 to get to that mean of 4? 1 times 1 plus 3 times 0 plus 6 times 0. This is going to simplify to yi equals 4. Does that make sense? So what I can look at here is that these represent not the constant. The constant is the mean of the referent group. Right? And if I excuse me, I interpret these slopes as I had before. For every 1 unit change in x, this is the expected value change in y. So as I go from the daily group to the other group, how much do I have to change to get the expected value? And by definition, the expected value is going to be the mean, right? So these coefficients are nothing more than mean differences. And these t-tests here, these t-tests represent, are these coefficients, are these group mean differences statistically significant? So here we see that drug 4, which is the placebo group, is the only one that's statistically significant. Right? Does that make sense? Yes, no? No, let's do it another way, okay? Let's do it another way. All right, so what I'm going to do next is I'm going to drop the drug. So now I'm back to my original data set, okay? All right, and then what I'm going to do is I'm going to set up the contrast matrix the way that we want it to be. I don't care about the difference between daily versus all these other things, right? That's not what we said. We wanted to compare everything else against placebo. So how are we going to do that? Well, I need to create a series of my predictors from my model. I need to create a series of predictors for my model. So the first thing I'm going to do is I'm going to choose what my predictor is going to be. All right, so what I'm going to do here is I'm going to say I'm going to create a new variable. I'm going to create this new variable. I'm going to call it x1. And then I'm going to do a test, right? So everything here is a test. So I'm saying, does drug equal 1? And remember, we coded this as 1, 2, 3, and 4, right? So I'm going to say, does drug equal 1? So if that's true, the computer is going to say, yes, that's true. Give x1 a value of 1, otherwise it's false. And if it's false, it's going to give it a value of 0, right? So this is Boolean logic. Boolean. Okay? So that's what I'm going to do. That's what I'm going to do for each of my predictors. Now, when I do my list, now I have my referent group as having all of its x's equal to 0. Now the placebo group, the no drug group, becomes my referent group. Make sense? x1 is going to represent the effect, the relative effect of receiving the drug daily versus the referent group. Right? x2 is going to be the relative effect of receiving the drug weekly versus the placebo group, and x3 is going to be the relative effect of biweekly versus no drug. Make sense? So now when I do my regression, one thing you'll notice up here, none of these values changed. It's the same ANOVA as we did before. Nothing changed up here. Not a thing has changed.
So can you say again, what different question are you asking by doing it this way instead
as opposed to just doing the ANOVA? So now instead of looking at all possible pairwise comparisons, which is, what, 6 in this case, I now come to the study with a very specific research hypothesis.
Oh, to the referent group.
Yes, now I'm saying, are there any differences between active drug as compared to placebo, as compared to the no drug group? Okay. So now, all of my coefficients have changed, right? All the coefficients have changed. So what do I see? Now I see my constant as being a 9. What's the 9? That's the mean of my referent group, right? Now I see this -6, right? If I were to do 3 minus 9, that is the mean difference between the daily group and the placebo group, right? Does that make sense? So the reason that we're going through this exercise is because if you understand how to do the regression, you can ask a very specific question of your data, set up your very specific contrast, go into your study with your very specific question, and you don't have to pay such a large penalty for using those post hoc tests. And oh, by the way, the ANOVA is still the same. You've still done an ANOVA. Now you're asking a very specific question of the data. A very specific question of the data.
So 2 quick questions. So the coefficient numbers, like, what do they, I mean, I get that you can look at the p-values and like see if they're significant or not, and then tell you relationships in your data. What about these coefficient numbers?
What? Here?
Yeah.
Okay, let's
Absolutely
absolutely it does. Right, that, yeah, so let's look at it here, right? So let's write this all out. All right, so we have placebo. This is 9. So what I'm going to do is I'm going to subtract 9 from each of these things, right? So this is going to give me minus 9 is going to equal -6. Minus 9 equals -5. Minus 9 equals -3. 6, 5, 3. These are the group means. So if you were to ask the question, is the difference between the amount of food eaten when I compare the rats in the placebo group versus the rats in the daily group, on average, the rats in the daily group that consumed 6 pounds fewer, or 6 pounds less, than did the rats in the placebo group. And that difference is statistically significant. This is the confidence interval around that difference, that group mean difference of -6. So remember we said, if you had a bunch of groups, you could do a bunch of t-tests. This would not be the same exact results of your t-test, because when I compute my standard error, the standard error is going to be based on 12 degrees of freedom. It's going to be based on a different number of degrees of freedom. But it's the same exact hypothesis.
But this is more precise.
It's more precise.
So what if I wanted to make the daily group my
Okay.
group reference?
Okay, let's, how about we work on this together? All right, so now you're going to ask a different question. So essentially what you're asking is daily the best? Right, that's essentially what you're asking, right? So let's work on this together. All right. So I have K equals 4, right? I have 4 levels of my factor. How many X variables do I need to represent my 4 levels? I'm still going to need 3, right? So I'm going to need an X1, an X2, and an X3. All right, and does it matter the order? And let's change the order in which I write down the levels of the factor. So what do we want our first one to be? All right, bi-weekly, weekly, daily, and placebo. Right? And the question is now we want to make the daily the referent group, right? We want to make the daily group the referent group. So what did we say we're going to do once we've decided on what our referent group is going to be?
It's going to be all zeros.
Those are going to be all zeros. Okay? The reason I've changed the order of these things here, because it doesn't matter. right? It doesn't matter what the order is going to be. So what do we want x1 to represent? It doesn't have to be biweekly. It can be whatever we want it to be. Let's make it placebo. All right? And what do we want x2 to represent?
Bi-weekly. Bi-weekly.
Bi-weekly. We want x2 to represent bi-weekly, which leaves weekly to be extra. We didn't have a choice, right? Okay, so let's do it that way, and we'll see what happens. Before we do that, I bet we can predict what's going to happen, though. These are going to be your coefficients. That's going to be your intercept. Okay, so x1 is going to be placebo, so that's drug 4. x2 we said was going to be biweekly. x3 we said was going to be weekly. Did the ANOVA change? The ANOVA did not change. What changed? The coefficients changed because the x, now we have taken control of the computer, which, by the way, is what should happen. Like, you're telling the computer what to do as opposed to you simply accepting what the computer tells you, right? Now we know to interpret this x1 as being the effect for placebo as compared to our reference group, which is going to be daily. All right? We see that the placebo group ate 6 pounds more food than did the reference group, in which case that's the daily group. That's statistically significant. Oh, by the way, right, that's still statistically significant. X2 is going to be the effect of biweekly compared to daily. That's a difference of 1, just as we predicted it to be. Right? Not statistically significant. And then we have x3, which is the effect of biweekly as compared to daily. That's a difference of 3, not statistically significant. Right? So, yeah.
How do you code this again? You dropped. Well, you had to drop the.
Yes, because I kept using x1 and I just doing x3 over and over again. So how did we? The question is, how did we take control? How did we take control? Okay. So we have to decide what our reference group is going to be. And all I'm going to do is I'm just going to create my x's. I didn't have to call it x1, x2, and x3. It's just easier when I write it down that way, right? I could have called this Fred, Dino, and Wilma. Right?
But then 4 will always be, that's what we assign
to group
initially.
1. Yes.
Yeah.
So you have to understand how your factors were coded.
Okay.
Right? So imagine that you actually have to understand your data, which is why we spend all that time looking at the univariates and does it make sense and blah, 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 blah. Right? So if I were to simply accept the default behavior of Stata, it didn't give me the answer that I wanted. Right? It didn't give me the answer that I wanted. But now that I understand this model and how to parameterize it, now I can ask whatever question I want.
Explain why it didn't give, when you first do just the first line after dummy code.
Here, this?
Yeah.
Yeah, what Stata does is it defaults to having the lowest value be the reference group. And in this case, the lowest value, we coded these as follows: 1, 2, 3, 4. So it made, because daily was coded the lowest, ordinally the lowest, it made it the reference group. That's not my question.
What, wasn't that a question?
Well, eventually it was.
But that actually gives a different.
Does it?
Oh no, I see. It's just the order. So.
It's just the orders, the coefficient. This is why it's important to understand what each of these x's, what each of the parameters mean. right?
And do we code our factors up in the, when we said label define, like that line, or when did we code our?
When we read in the data,
Yeah, like right in the beginning.
up here, 1, 2, 3, 4, that's when it takes on the numeric values.
And then we said label define, 1 is something.
1 is daily.
Right, so that's where we got our little.
Well, this is, no, this is what Stata stores. If you were to say,
Okay.
if you were to say gen x1 equal drug equal daily, Stata would throw up. Because this is text, but Stata knows that drugs is numeric, as opposed to text or a string. Right? So you have to understand how the data are, right? Right, so all these exercises that we did way back when in Stata Lab of defining and understanding your data, it's all important. It's all very important because ultimately all that work that you did up front to come up with the labels and understand the meaning of your data, without that understanding, how the hell do you interpret the output of a regression that's just going to kick out a bunch of coefficients? You really have to understand what it is that your computer is doing. Or you could just take the easy way out and just do a post hoc, but you lose power. You lose statistical power. Right? Okay. Okay. Let's do something else that is a little bit interesting. This is actually how you would do using something called deviate coding. But let me before we do that, I want to bring your attention to something here. If I were to sum all of these columns, they all sum to 1, right? They all sum to 1. That's true only when we have dummy coding. Dummy meaning yes, no. Okay? There are lots of other ways that we can parameterize the model that I want to talk about. Right? A second way that we can parameterize our model is something called deviate coding. Deviate coding.
Can before you do deviate, can I ask you a question?
Mm-hmm.
So is there another reason besides, so all I've got in terms of why you do dummy coding is so you can change the reference variable?
Yeah.
That's the only thing you're doing?
Mm-hmm.
And then what I don't understand is what about what you're doing is a priori rather than post hoc?
You have defined,
what's the hoc, right?
Yeah, what's the hoc part,
Yeah.
right? Well,
So now, right, the data is
the post hoc stuff, the stuff that we did last week, you had a hypothesis, and it said that there's at least one pairwise difference. It wasn't specific. So because you sort of have this nebulous, ambiguous hypothesis that you're testing, you pay a significant statistical penalty for lack of specificity. So when you were to use Bonferroni or Sheffies or Tukey or the LSD or whatever test that you're going to use, it becomes much harder to reject the null hypothesis for any one of those comparisons. What we've done today is we've said, okay, now I understand something about my data. I'm a little bit farther in my program of research. So instead of asking the question, are there any pairwise differences?
Right.
I'm going to ask a far more specific question.
Right.
I'm going to ask a question a priori, beforehand. This is the question that I'm interested in.
Before you run the numbers.
Before you even do the experiment, you should write down, before you look at your data, before you do anything, you should write your analysis plan. Because you really do get credit for it. You get scientific extra credit, if you will, by saying, I'm going to go out on a limb, and I'm going to make this very specific hypothesis. And therefore, I should get credit for going out on the limb, as opposed to saying, I don't know what the hell's going on, I'm going to look at everything and see what's significant. So it's data dredging versus hypothesis testing.
So what you're doing up here is you're picking the reference variable,
Yeah.
which specific comparisons are
Yes.
important.
Yeah, exactly. Okay. Now, the next thing I want to talk about is something called deviate coding. Now, we've seen this word like only a gajillion times, right? What is a deviate? Some observed value minus an expected value, right? It's essentially what all of statistics is about, really. That's really what statistics is about, right? And we said that the ANOVA is a little bit different because we look to add within groups and between group sources of error, right? And in our model, the between group source of error is what we model, right? And then we wrote down the sums of squares for our between groups like this, right? Remember we wrote that down? We did it by hand. So this is x bar dot j minus x bar dot dot, which is what? That's the degree to which the group means vary around the grand mean, right? This is what we're modeling in the ANOVA. So what's going to happen here is our model stays the same. I'm going to write it down the same, right? What's going to change, again, is the meaning of the coefficients, right? So if I have a deviate, what's a deviate? It gives you two pieces of information. It gives you distance and direction from a mean. So if I'm doing between groups comparisons, what's the mean going to be? We just wrote it down. X bar dot j minus x bar dot dot. It's going to represent the overall mean. So what's going to happen in deviate coding is that beta 0 is going to represent the grand mean, and these betas are now going to represent deviates from that grand mean, which sounds an awful lot like ANOVA. So when the people who were doing ANOVA discovered this regression thing, they were like, oh, how do I make this regression in ANOVA work the way that my mind works? And their mind works x bar j dot minus x bar dot dot. Right? So what's going to happen here is I have k groups. How many dummy variables am I going to need to represent each of those k groups? K minus 1. So in this case, I'm going to have x1, x2, x3. Is anybody seeing a pattern here? All right, I keep saying to you guys it's just all the same stuff. Okay, all right. So I have my daily, my weekly, my bi-weekly, my placebo. So here I need to do as I did before, I need to pick a reference group. So let's pick a reference group.
Placebo.
Huh?
Placebo.
Again, you're so boring. Okay, so for placebo, instead of zeros, we're going to represent our reference group as -1. Okay? And this will make sense in a second as to why we call it deviate coding. So then, I won't bore you by asking you the same questions again, but I'm going to code it this way. Okay? So here I'm going to let x1 represent the effect for daily, x2 is going to represent the effect for weekly, x3 will represent the effect for bi-weekly. What happens when I sum the columns now? What happens when we sum deviates? Always. Bada bing, bada bing, bada bing. Okay, all right, so let's do that. All right. So all I'm going to do is I'm going to use the same logic as I did before. All right. So how am I going to do this deviate coding? I'm going to say gen x1 equal drug equal 1. That's going to return a 0 and 1 variable. And then I'm going to replace my x1, I'm going to set it to -1 if drug is 4, the placebo group. And I'm just going to do the same thing as I did before, okay? Okay. And then I'm just going to do my regression with my x's. Okay. So now, oh, what have we noticed about the ANOVA?
Same.
Hasn't changed. What's changed? The coefficients. Now, I have this intercept of 5.5. What the hell is that intercept of 5.5? Well, let's do this. We can do this easily because these are equally weighted. So 4 times 3 is, or 4 plus 3 is 7, plus 6 is, plus 9 is 22. Divided by 4 ought to give me 5.5, right? So now the intercept for the model parameterized this way is the overall mean. It's the grand mean. Okay? So how do I interpret each of these things? Well, let's see here. What happens when I subtract 5.5 from each of my values? What happens when I subtract 5.5 from 3? -2.5. What happens when I subtract 5.5 from 4? What happens when I subtract that? That's what these things mean, right? So now these p-values are a little bit goofy, right? So now what is the hypothesis? This really drives home the idea of what analysis of variance is, I think. So if these things are deviates from the grand mean, what analysis of variance is saying really is there any variance around the mean that is statistically significant? Because if all of the group means were the same, right? If all of the group means were the same, they would equal what? The grand mean. There would be no variability around the intercept. That's what ANOVA is. The reason I'm showing you this, right, is because depending on who you talk to, and you'll talk to a lot of different types of researchers in your career, people are going to parameterize their models differently. Some people may do this deviate coding because that's how they were trained. Some people are going to do this dummy coding because they're either lazy and they're just going to accept the defaults of the software, or that's how they were trained. So the reason I'm showing you these different ways to parameterize the model, and by the way, you get the same results, is that now you can have conversations with people in their language, right? In their language. In medicine, you'll get people from the social sciences, you'll get people from the hard sciences, you'll get all kinds of people who are contributing to the body of literature. And to be able to have a good, intelligent conversation with them, I have found, instead of forcing them to think like me, which is scary, I try to adapt to their way of thinking because I can do that translation in my head and know that all of these things are equal. Okay?
Using our example, what specific question does this answer?
This answers the question, is there significant variability around the grand mean? Which is the ANOVA question.
So is there any difference between the ANOVA and this?
No, this is
the ANOVA.
The ANOVA
Okay.
in regression.
Okay.
Right? But we're seeing that no matter how we set up our contrast matrix, we get the same this up here. We get the same ANOVA. But if we were to get the xij or x dot j minus x dot dot, this is what we're getting. Yeah.
I'm confused with the referent group, and when you did this, you defined it as -1
Yep.
instead of 0. I missed why we did that.
Because that's what we need to do deviance. Notice our column sum to 0.
Okay.
All right, this is going to blow your mind, right? You're like, where the hell does this -1 come in, right? Let's write this out. All right. So I have yi equal 5.5 plus, what's beta 1? Minus 2.5 times x1 plus minus 1.5 times x2 plus 0.5 times x3. Okay? This is just regression. I want to predict yi. Let's predict the yi for the person in the placebo group. You ready for this? Because this is cool. I think it's cool. Minus 2.5 times -1. Minus 1.5 times -1 plus 0.5 times -1. Let's do it out, right? So this is going to be 5.5 plus 2.5 plus 1.5 minus 0.5. This is going to equal
8.
Huh?
Nope, 9.
No, you're right. 8 plus 1.5, 9.5 minus 0.5 gives me, which is the mean of the placebo. Is that not the coolest thing? No, I think it's cool.
So if you're comparing everything to the grand mean,
Yep.
does it matter which row you make your
Okay.
referent group?
No.
Because this is just ANOVA.
This is the ANOVA.
So why would you do this over just
Well, I wouldn't.
Okay.
Other people might.
Okay.
And if they do,
So it's just a way to understand
Yeah.
if people are using this. You'd be
Yes.
like, well,
yeah. This actually becomes, this deviate coding actually becomes really important when we get to things like decision theory and things like logistic regression. Because what can happen here is in logistic regression, oh, by the way, all of these coding ways that we can use, you can use these coding methods in all kinds of regression. It's not just for linear regression. I actually use deviate coding when I do decision theory models. So I'll do benefit risk studies with patients, and I'll say, here's this drug, it's got these wonderful positive attributes, but as with anything good, it's got these shitty attributes too. And then you can begin to quantify the utility. Have you guys talked about utilities? How important or how valuable each of these attributes are compared to everything else, right? So what happens here is that each of these coefficients then become utilities in a logistic regression for deciding on you want to use this versus that, taking everything else out and taking everything else into account. Okay? Okay? All right. So the last thing we want to do is let's really think about the property of our data here. 3, 4, 6, 9. Now, say you're a money-grubbing, greedy pharmaceutical company. Not that they exist, but let's say that you are. Right? And you were to take into account the ordinal nature of the data. Can you think of any other interesting kinds of questions that you might ask of the data? I might ask a question like, well, is daily better than a combination of everything else? Right? And then I might say, okay, well, if that's not true, then I might ask the question, well, is weekly better than everything below it? And then I might finally ask the question, is biweekly better than placebo? Now that is a very specific hypothesis. Now I'm talking about this versus everything else, the next thing versus everything else, and the next thing versus everything else.
And you took the daily out of the weekly ones that
Yep.
you've already looked at.
Yep, because I've already looked at is daily better than everything else. Okay, take that out. I've already answered that question. Now, is weekly better than everything else? Right? Excluding daily, because I've already looked at that question, right? Now, think about it this way. Could you then prioritize the order in which you do these comparisons? You absolutely could, just like we messed with the order of our parameter estimates with the regression. We changed what reference group we wanted and all that. We could do all that, right? Do whatever we want, right? We could do whatever we want, more or less mathematically. But what I'm trying to get you guys to think about is be very specific with your questions. Because what I could do is I can say, first and foremost, is daily better than everything else? Because that's really the question I want, right? Because if I'm a money-grubbing, greedy pharmaceutical company, I might say, ha, this is better than everything else. Let's give the drug daily, right? Even though maybe there's no difference between weekly and daily.
My question was, is daily different for everything else?
That's the question, but it's a combination of everything else. So what's going to happen, the way that we code this, is daily is going to be left alone, and then weekly, bi-weekly, and placebo will be collapsed into one group. Right? So in that comparison, there is no difference between weekly, bi-weekly, and placebo, and so on and so forth. Okay? But from a policy perspective, right, you might say, difference in socioeconomic groups or something like that, right? Because we can think about some ordinal nature of socioeconomic status. Is the high group better than everybody else? Is the next highest group better than what's left, and so on and so forth, right? So now you're beginning to ask very specific, more and more specific questions of the data, right?
So if you find that daily is better than everything else, do you then break everything else into the weekly, bi-weekly, placebo to find out where the difference really is?
Well, no, because you could, but I might not be interested in that question. It depends on how you frame your question. When I do this analysis, it's going to be daily versus everything else. That's what X1 is going to test. X2 will be daily versus biweekly and placebo. X3 will be biweekly versus placebo. X1 will be daily versus the combination of weekly, biweekly, placebo. X2 will be weekly as compared to biweekly and placebo. X3 will be the difference between biweekly and placebo. We call this Helmert coding, H-E-L-M-E-R-T.
Helmert or reverse Helmert?
It actually doesn't matter because if you look...
I'm just reading the code.
No, because if you look at it, all I did, the reverse Helmert is simply asking, is placebo different from everything else? I just went the other way. That's all I did.
And then back up.
Yep. Okay, so there's a special way that we're going to code this. There's a special way that we're going to code this. And I'm going to teach you a way to do Helmert coding that I think I have found in maybe 2 books. So let me show you what's going to happen. There are a couple of ways that we can do this. I'm going to show you the way that most books will teach you. And then I'll show you the better way, the more interesting way. Okay. So this is how most software does its Helmert coding. So here what I'm going to do is I'm going to say daily is going to take on the value of 3. The remaining groups are going to equal negative values that sum up to 3. Because the column is going to sum to 0. Okay? For my X2, I've already done my question about daily. I'm not interested in the variance due to daily in my X2. I'm going to give this a value of 2. And these two we're going to sum to whatever it needs to sum so that the column sums to 0, and so on and so forth. Okay? The problem with coding this way is that the ANOVA will become correct. The p-values from the regression coefficients will absolutely be correct. But the parameter estimates, where it says coef up there, they become very difficult to interpret because they're all over the place. Okay? So what I'm going to show you is a different way to do this. So that the coefficients have a very natural and intuitive meaning. So what's going to happen here is I'm going to code this value as 3/4, -1/4, -1/4, -1/4. Right? Still sums to 0. 0, 0, 0. 2/3, -1/3. Still sums to 0. Half, -1/2. Now, by coding the data this way, the parameter estimates will have a very natural and intuitive interpretation. By coding the data this way, the coefficients will actually represent the group mean differences, just as we did in the past with, just as we did before. Okay? So let's code it this way. And we'll see what happens. First of all, let's look at the intercept. Always going to represent the grand mean because our columns sum to 0. Okay? So what does this -3.33 represent? What is, so I'm going to get the mean of these groups combined. So what's 19 divided by 3? 6.3, I bet. Something like that, 6 1/3, right? If I subtract 3 from 6 1/3, I get 3 1/3. Now let's do the second one. 6 plus 9 is 15 divided by 2 gives me 7.5, right? 4 minus 7.5, that's a 5. Ought to give me what, -3.5? See how this works? But think of the possibilities. Think of the very interesting questions that you're going to ask armed with this knowledge to be able to do this sort of thing, right? And then finally, the last one is going to be biweekly versus placebo. -3, right? So that's how that works. Okay? So all of that work that we did, learning about deviates and they sum to 0 and all that stuff, like if you really understand it, you can ask incredibly precise, incredibly powerful questions of the data. So what I'm going to encourage you to do, and I will always encourage you to do this, is to be creative and ask very specific questions of your data. Because if you can ask those very specific questions of your data, with a little bit of creativity, you can figure out how to write out the model to answer that specific question, as opposed to, using a shotgun and trying to blow holes in the data and go, oh, that's interesting. I didn't look for that. That wasn't my primary question, but we'll look at that over there. Right? So with a little creativity, armed with this knowledge, you can really answer very specific questions and push the state of the art of your discipline very far with some thought. Okay? All right. So here's what I want to do next. Next Thursday, we'll pick up with logistic regression. So in the meantime, I will post some slides up there that we'll use as the motivator for Thursday, okay? Okay, all right.
We have that tomorrow?
Yeah. So what we might do tomorrow for lab is
He
we'll take
said that
another
the
data
final is
set,
basically gonna be,
a different ANOVA
here's a
data
data
set,
set,
and we'll do this sort of,
interpret it, like what he's been
Together.
doing with the last couple ones, like with the logistic regression.